If you have ever looked carefully at icicles in the wintertime, you would probably have noticed that many of them have this regular pattern of ripples around their circumference, which have a wavelength of about 1 centimeter. In this paper, we present an experimental study that explores the origin and evolution of these icicle ripples. So to do this, we built a tabletop machine for growing icicles that allows us to control the temperature, water supply rate, and air motion around the icicle. We rotate the icicle very slowly while it is growing, so we can distribute the water evenly around the icicle to encourage axisymmetry, and the rotation also allows us to image and analyze the different sides of the icicle. Here are 3 icicles grown under identical conditions, except for the concentration of sodium chloride dissolved in the water. The movie on the left shows a Stillwater icicle, which has a platonic shape with a relatively smooth surface. The movie in the middle is an icicle made from a solution that has only 40 milligrams of salt per kilogram of water, and we can see that even such a tiny amount of ionic impurities can produce a clear, regular set of ripples. The movie on the right shows a much more saline icicle, which deviates the furthest away from both axisymmetry and self-similarity. So using image analysis and Fourier methods, we found that growing ripples are not present on distilled water icicles, even when we saturate the water with dissolved gases. Growing ripples are also not produced when we add Triton X100, which is a non-ionic surfactant that we use to reduce the surface tension of the water. On the other hand, ripples appear on icicles made from saline water, even at very low concentrations. The ripples on more saline icicles grow faster to higher amplitudes, although the ripple amplitude can also decrease after it has saturated. We also found that at sufficiently low salinities, the growth speed of the ripples increases with the salt concentration. This increase is roughly logarithmic, which is very weak. Below about 0.05 weight%, the ripples climb up the icicle uniformly at a speed of a few millimeters per hour, but above 0.05 weight%, the ripple motion becomes more nonlinear, and different ripples on the same icicle can travel in opposite directions. There have been a couple of theories trying to explain the formation of icicle ripples, but none of them has considered the effect of impurities, which we have shown experimentally to be the most significant control parameter in this problem.